Welcome to another episode. It's always a joy to have you here. Before we begin tonight's journey, I'd love to know, where are you listening from and what time is it there? You can leave a comment below, and if you haven't yet, consider subscribing. It helps this calm space of curiosity and slow discovery continue to grow. Now, imagine the invisible threads that hold the world together. They shape the way planets move, how light bends, how a single drop of water ripples across a pond. They define the curve of a seashell, the orbit of a moon, the way your heart keeps its rhythm. And though we cannot see them, they're everywhere, hidden in plain sight. Mathematics, the quiet language of the universe. Older than writing, more precise than any spoken word. It doesn't belong to a single culture, yet it unites them all. From ancient stones etched with numbers to modern computers tracing the edges of infinity. Through mathematics, we've learned to measure, predict, and dream, to glimpse the deep architecture of existence itself. So, if you're ready, let's begin our journey into the mathematics that shaped the universe. Long before mathematics had symbols or equations, it began with something much simpler. A need to remember, to measure, to make sense of change. Somewhere in Central Africa, nearly 20,000 years ago, a small piece of bone was carved with a series of notches. It's known today as the Ishango bone, discovered near the headwaters of the Nile, and dating back to around 18,000 to 20,000 BCE. The notches aren't random. They appear in deliberate groups, sets of tallies that may have recorded lunar cycles, or perhaps quantities of food or game. It's one of the earliest known artifacts of human numeracy, proof that long before writing, before civilization, we were already counting. These markings tell a quiet story, that mathematics didn't begin in laboratories or palaces, but in survival. The first mathematicians were hunters, gatherers, and farmers, people who needed to track the seasons, to know when the rains would come, or when the moon would return full. Every line carved in bone, every pebble laid in a row, was a small step toward abstract thought, toward the idea that one thing could represent another. As communities grew, counting became communication. In ancient Mesopotamia, between the Tigris and Euphrates rivers, clay tablets bear the marks of accountants, literally. Sumerian merchants pressed reed styluses into wet clay to record quantities of grain, livestock, and silver. Here, in the cradle of civilization, mathematics became an instrument of order, a way to organize life itself. The Babylonians took it further. They used a base 60 system, sexagesimal, which might seem strange today, but you still carry its legacy. When you glance at a clock and say that an hour has 60 minutes, or a circle has 360 degrees, you're echoing the same numerical rhythm the Babylonians used more than 4,000 years ago. Their system was elegant. 60 divides neatly by 2, 3, 4, 5, and 6, making it perfect for fractions, ideal for trade and astronomy alike. They recorded the paths of planets, calculated eclipses, and even approximated what we now call pi, the ratio of a circle's circumference to its diameter. For them, mathematics was both practical and divine, a way to align earthly life with the heavens. Farther west, the Egyptians developed their own arithmetic, one built from the geometry of the Nile. Every year, the river flooded and erased the boundaries between farms. So surveyors, the harpedonaptae, or rope stretchers, would measure again, stretching knotted ropes across the fields to restore order. Their geometry was born not from theory, but from mud, from the rhythm of flood and renewal. They built pyramids with extraordinary precision, aligning them with the stars and the cardinal directions, guided by right angles and ratios long before Pythagoras would give them names. Even their hieroglyphic numerals reflected a world rooted in the tangible. One stroke for one, a coil of rope for 100, a lotus for 1,000. To count was to visualize the world. Across the ocean, civilizations we often think of as isolated were creating number systems of their own. The Maya of Central America used a base 20 system, vigesimal, counting not just on fingers, but on fingers and toes. Their numbers were written in elegant combinations of dots and bars, and they were among the first to use a symbol for zero, a small shell representing nothing, yet everything. This concept, zero, would take millennia to reach Europe. It's a simple idea that changed the world, the ability to represent absence as a number, to make nothing into something that could be used, moved, multiplied. Meanwhile, in ancient Rome, numbers marched with legions. Roman numerals were practical for record-keeping, but limited for calculation. You could add and subtract, but not multiply easily. They were numbers for empire, not for discovery. Still, they left a mark that would outlast the empire itself, carved in stone on temples and clocks, symbols of permanence. Through these early ages, a quiet transformation was taking place. Mathematics was no longer just a tool for counting sheep or measuring fields. It was becoming a language of thought. When humans began to see that numbers could describe not only what they had, but how things behaved, a new kind of understanding emerged. A shepherd counting flocks might notice patterns in births and losses. A builder might observe that certain shapes made structures stronger. From these realizations came the first steps toward abstraction, the recognition that patterns exist beyond the things themselves. That leap, from practical counting to conceptual reasoning, was one of humanity's greatest. It's the moment mathematics began to detach from the physical world and reach into the invisible. No longer tied to crops or trade, it became a way of thinking, a mental tool to imagine what couldn't be seen. With it came a new kind of freedom. Once we could represent quantities with symbols, we could manipulate them, experiment with them, discover hidden relationships. Mathematics became a place where the mind could wander without boundaries, where imagination met logic. And yet, even in its earliest forms, it carried something almost spiritual. Numbers began to suggest a secret order behind the chaos of life, an unseen rhythm, a balance, a harmony. Every time a farmer divided land into equal parts, or an astronomer watched the moon's perfect cycle, they were brushing against a truth too large to name. From those first carved bones to the sand-smeared tablets of Sumer, from the star charts of Babylon to the pyramids of Giza, mathematics was teaching humanity to look deeper, to find meaning in measurement, to see the infinite in the finite. We tend to think of mathematics as cold, logical, detached. But in its beginning, it was deeply human, born of hunger, weather, love, and fear. It was the quiet heartbeat of civilization before civilization had a name. And from these humble beginnings, from bone and clay and rope, a new kind of curiosity would soon emerge. One that asked not only how much, but why. A question that would echo across millennia, from ancient Greece to modern physics. Because once we began to count, we could never stop. When we think of ancient Greece, we often imagine marble statues, philosophers in white robes, and sunlit temples. But beneath all that beauty, there was a revolution taking place, one not of politics or conquest, but of the mind. It was in Greece that mathematics first became philosophy. By the 6th century BCE, thinkers along the coasts of Ionia, in what is now Turkey, began to ask questions that no one had asked before. One of them was Thales of Miletus, often called the first true mathematician. He's remembered less for what he calculated than for how he thought. According to legend, Thales once measured the height of the Great Pyramid simply by observing the length of its shadow and comparing it to his own. It wasn't magic, and it wasn't guesswork. It was reasoning, a recognition that nature could be understood through proportion. He is said to have predicted an eclipse, studied geometry in Egypt, and, more importantly, tried to explain the world not through myths, but through principles. That was new. In a world where lightning was the anger of gods and stars were eternal fires, Thales suggested that there were patterns, that behind the apparent chaos of the universe lay something measurable, something comprehensible. He believed that water was the fundamental substance of all things, but what truly mattered wasn't his conclusion. It was the idea that reality could be reduced to underlying rules. He was beginning to treat the universe as a system that could be reasoned with. From Thales came a lineage of thinkers who saw numbers not just as tools, but as symbols of truth. Among them was Pythagoras, a figure surrounded by both legend and mathematics. He founded a community that blended philosophy, science, and mysticism, a brotherhood that believed numbers were the essence of all existence. For them, mathematics wasn't a human invention, it was the structure of reality itself. Pythagoras taught that harmony in music, the pleasing sound of an octave or a fifth, could be expressed through ratios of whole numbers. Two strings, one twice the length of the other, produced a sound that was not random, but beautifully related. To the Pythagoreans, this was evidence that the universe itself was harmonious, that beauty and order flowed from numerical relationships. They saw number as divine. Of course, their fascination led to both wonder and crisis. When one of Pythagoras's followers, according to legend, discovered irrational numbers, lengths that couldn't be expressed as simple fractions, it shook their belief that the cosmos could be reduced to neat ratios. These numbers, infinite and incommensurable, were proof that even in a world ruled by mathematics, there were mysteries beyond understanding. Yet rather than abandoning their search, the Greeks pressed deeper. They turned mathematics into an instrument not just for measurement, but for logic. By the time Plato founded his academy in Athens, around 387 BCE, the idea that mathematics revealed a deeper reality had taken root. Plato, influenced by the Pythagoreans, believed that the physical world was only a shadow, a reflection of perfect, eternal forms. Geometry, he said, was the bridge between the visible and the ideal. Above the entrance to his academy were inscribed the words, "Let no one ignorant of geometry enter here." To Plato, studying geometry was not about solving problems. It was a form of purification, a way to train the mind to see truth. For him, a circle drawn in sand was never a perfect circle, but it pointed to the idea of perfection itself, the invisible ideal of a circle that no craftsman could ever carve. Numbers and shapes were not mere abstractions. They were glimpses into the fundamental order of the cosmos. In this way, mathematics became philosophy's most sacred language. The Greeks were not simply counting anymore. They were contemplating the very structure of existence. Out of this culture of pure thought came one of the most remarkable works in human history, Euclid's Elements. Written around 300 BCE, it gathered the mathematical knowledge of the ancient world into 13 books, carefully organized and logically built from first principles. Euclid began not with equations, but with axioms, simple, self-evident truths like things equal to the same thing are equal to each other. From these foundations, he constructed a universe of logic. Every theorem, every geometric truth, followed inevitably from what came before. It was the first time in history that knowledge had been built as a complete system, one that could stand entirely on reason. For more than 2,000 years, the Elements was the gold standard of rational thought. It shaped not only geometry, but philosophy, science, and even the way we define proof today. To read Euclid is to see the birth of structure itself, the idea that from a few simple rules, an entire cosmos of understanding can emerge. And yet, even among the Greeks, not all mathematics stayed in the realm of abstraction. One of the greatest minds to ever live, Archimedes of Syracuse, united the purity of theory with the brilliance of application. He was a mathematician, physicist, engineer, and dreamer all at once. While Euclid built worlds on paper, Archimedes built them in bronze and water. He discovered the principles of buoyancy, calculated the value of pi with astonishing accuracy, and designed war machines capable of defending cities. He once wrote, "Give me a place to stand, and I will move the earth," referring to the power of the lever, a simple mathematical principle of proportion and balance. In his mind, mathematics wasn't confined to scrolls. It was a living force that could lift worlds. He also pioneered ideas of infinitesimals, the conceptual ancestors of calculus. By dividing shapes into infinitely small parts, he could find their area or volume long before Newton or Leibniz formalized the method. It was the birth of mathematical infinity, the realization that the infinite could be approached through logic. For the Greeks, mathematics was not merely about finding answers. It was about understanding why those answers were true. They cared less for results and more for reasoning. Proof became sacred. To show that something was logically necessary, that it could not be otherwise, was the highest achievement of the mind. Their obsession with harmony, proportion, and proof transformed human thought. It was in this age that mathematics became synonymous with truth itself. A sculpture or a melody could be beautiful, but a theorem was perfect, unchanging, eternal. The Greeks saw the universe not as a chaos of matter and motion, but as a grand design waiting to be revealed through reason. Every triangle, every ratio, every circle was a key to understanding existence. This belief would echo through millennia. When later scientists like Galileo and Newton described nature mathematically, they were carrying the torch lit in ancient Greece. The idea that the laws of the universe could be written in numbers, that geometry could describe gravity, or that algebra could capture light, all began with the Greeks' conviction that the world was rational. Yet what makes this era so extraordinary isn't just what they discovered, but how they thought. They believed that the human mind could reflect the logic of the cosmos, that through reasoning alone we could touch something eternal. It was an audacious idea, that truth was not hidden in the heavens, but could be found within thought itself. For the first time in history, knowledge was being pursued for its own sake, not for profit, not for survival, but for wonder. Mathematics became a form of devotion, a meditation on perfection. And in the process, humanity changed forever. From Thales measuring shadows, to Pythagoras hearing the music of numbers, to Euclid drawing flawless proofs, to Archimedes balancing the earth on logic, the Greeks transformed mathematics from a craft into a cosmos. They showed that behind every line and curve lies something deeper, a reflection of reason itself. And that idea, that truth, can be reached through thought, that the universe is governed by principles we can understand, would become the foundation upon which all of modern science would rest. For all the brilliance of the Greeks, their geometry lived mostly on parchment, clean, perfect, unchanging. But out in the world, nature has never been quite so tidy. It spirals, cracks, folds, branches, and repeats endlessly, yet never quite the same twice. For centuries, humanity looked for beauty in symmetry and perfection. And then, slowly, we began to realize that nature's beauty was mathematical too, just in a different, wilder way. In the early 13th century, a man named Leonardo of Pisa, better known as Fibonacci, published a book called Liber Abaci, the Book of Calculation. It was meant to promote the Hindu-Arabic numeral system to merchants in Europe, but hidden inside was a simple puzzle about rabbits. He imagined a pair of rabbits placed in a field. Each month the pair produced another pair, and those pairs, in turn, grew up and multiplied. How many rabbits would there be after a year? The solution produced a sequence that looked like this: 1, 1, 2, 3, 5, 8, 13. Each number was the sum of the two before it. It seemed like a trivial counting problem. But over time, mathematicians and naturalists began to notice something strange. The same pattern appeared everywhere in the natural world. The spiral of seeds in a sunflower, the arrangement of leaves on a stem, the pattern of scales on a pine cone, all followed Fibonacci's mysterious sequence. If you look closely at a sunflower's head, you'll see spirals winding in two directions, one clockwise, one counterclockwise. Count them, and you'll often find that one direction has, say, 34 spirals, and the other 55, both Fibonacci numbers. Nature, it seemed, had a preferred way of organizing growth. The same ratios appear in shells, pineapples, hurricanes, even galaxies. From the very small to the very large, nature tends to grow by addition, building upon itself, one layer at a time, just as the sequence does. The deeper you look, the more elegant it becomes. If you take any two consecutive Fibonacci numbers, say 34 and 55, and divide one by the other, you get a ratio that approaches a value of about 1.618. This number has fascinated mathematicians, artists, and philosophers for centuries. It's known as the golden ratio, often written as the Greek letter phi. The golden ratio has a peculiar property. If you take a line, divide it into two parts, so that the ratio of the whole to the larger part equals the ratio of the larger part to the smaller part. Ratio of the larger to the smaller. That ratio is phi. It's a relationship that seems to recur throughout geometry and, many believe, in the natural world. The Greeks had already noticed its beauty. They called it the divine proportion. Architects used it to design temples. Renaissance painters built compositions around it. It was said to appear in the Parthenon, in Leonardo da Vinci's Vitruvian Man, even in the proportions of the human body itself. But here, myth and reality begin to blur. Modern research shows that while phi does appear in some natural growth patterns, its role in art and architecture has been exaggerated. The Parthenon wasn't deliberately built with golden rectangles. The idea likely came later, as people searched for order in what they already found beautiful. And yet, there's something poetic about that, because the human mind seems naturally drawn to patterns that echo the proportions of growth and balance found in nature. Even when we imagine them, we're revealing the same instinct that nature itself follows: harmony through proportion. Still, Fibonacci and the golden ratio describe only part of nature's mathematical story. Because while flowers and shells may spiral with graceful precision, much of the natural world is anything but smooth. Mountains are jagged, clouds curl and tumble, coastlines refuse to be measured cleanly, lightning forks through the air in patterns that seem random, but aren't. For centuries, geometry ignored these shapes. It preferred the perfect, the straight line, the circle, the sphere. But in the late 20th century, mathematician Benoit Mandelbrot gave us a way to describe the imperfect. He called it fractal geometry, the geometry of roughness, of recursion, of infinite complexity. Yet fractals existed long before computers or equations. They've always been written into nature. Take a Romanesco broccoli, for instance, a pale green vegetable that looks almost alien. Its surface forms a spiral of conical florets, each made of smaller cones, and each of those, smaller still, repeating the same structure down to the tiniest scale. Zoom in or out, and the pattern never really changes. It's self-similar, repeating itself endlessly within itself. You see the same thing in the branching of trees, in the network of rivers, in the pattern of veins across a leaf, in the filigree of blood vessels in your lungs. The branching follows mathematical rules, angles and divisions optimized for efficiency, for distributing nutrients, light or oxygen. It's mathematics doing what evolution does best, solving problems. Even chaos, when seen through mathematics, begins to show its own order. Look at lightning. It traces a path through the air, splitting, dividing, following invisible gradients of electric potential. Or consider the outline of a coastline. The closer you measure, the longer it becomes. Each inlet and cove hides smaller inlets and coves within it. Mathematically, this means the coastline's length approaches infinity as you increase your precision, a paradox that early geometers could never explain, but fractal geometry can. Fractals are nature's way of balancing simplicity with complexity. The rules are few, but the outcomes are infinite. A simple recursive formula, repeated millions of times, creates shapes that look alive. And perhaps that's no coincidence, because the same kind of repetition lies at the heart of life itself, in DNA, in cell division, in the branching of neurons inside your brain. Today, scientists study these patterns not just for beauty, but for understanding. Mathematics gives biology a language, a way to describe form and growth with precision. Physicists use fractal dimensions to understand turbulence and chaos. Biologists apply Fibonacci sequences to model how leaves arrange themselves to capture sunlight most efficiently, a phenomenon known as phyllotaxis. Even cancer researchers use fractal analysis to study the irregular geometry of tumor growth. Patterns once seen as merely aesthetic now reveal deep biological laws. Nature's mathematics, though, is not always tidy or idealized. Real plants deviate from perfect Fibonacci spirals. Clouds dissolve into unmeasurable shapes. Even the spiral galaxies that appear so graceful in photographs are turbulent, colliding, asymmetric. Yet within that imperfection lies the essence of reality, a universe that builds itself not from static laws, but from dynamic processes. Mathematics doesn't just describe nature. In many ways, it is nature. Modern physics takes this idea even further. In quantum field theory, the fabric of the universe behaves like a fractal sea, particles appearing and disappearing, fluctuations repeating at every scale. In cosmology, the large-scale structure of the universe, the web of galaxies and dark matter, resembles a vast fractal network, echoing the same recursive complexity found in a fern or a river delta. The pattern scales from the microscopic to the cosmic. It's humbling to realize that the same principles that shape a leaf spiral might also shape the distribution of galaxies across billions of light years. It suggests that mathematics is not an invention we impose on the universe. It's the rhythm the universe has always followed, long before we learn to listen. And yet, part of the beauty lies in the fact that these patterns remain imperfect. They remind us that mathematics, like life, exists in tension between order and chaos. A sunflower never has a perfect Fibonacci count. A snowflake is never perfectly symmetrical. And still, each one carries the unmistakable signature of mathematical law, softened by randomness, sculpted by time. To study these patterns is to glimpse nature thinking, to see its quiet intelligence. Fibonacci's rabbits, the golden spiral of a shell, the recursive branching of lightning, they're all part of the same great equation, written not in symbols, but in growth, energy, and evolution. When the Greeks looked for perfection, they found ideals. When Fibonacci looked at nature, he found recurrence. And when modern science looks deeper still, it finds something even more astonishing, that the universe may be self-organizing, using mathematics as its code. An endless feedback loop, generating beauty through necessity. In the end, perhaps that's what makes the mathematics of nature so calming and so profound. It's a reminder that even in chaos, there's rhythm. Even in randomness, there's order. And even in imperfection, there's something close to perfection. Something that quietly connects us to everything around us. From the spiral of a galaxy to the curl of a fern, from the branching of trees to the firing of neurons, mathematics is nature's handwriting. And every pattern we see is a whisper of the same infinite mind, that once shaped the stars. For most of human history, the universe was something we watched. We observed the stars, the seasons, the tides, and described what we saw. But in the early 17th century, a new idea began to take shape, that the universe wasn't just a stage for motion. It was a system that could be measured, predicted, and understood through mathematics. It was the beginning of a world that ticked like a clock. It started, in many ways, with Galileo Galilei. Born in Pisa in 1564, Galileo was both a physicist and a philosopher, though he would never have used the term scientist, because it didn't yet exist. What he did believe, however, was revolutionary, that nature followed laws, and that those laws could be written in the language of mathematics. In one of his most famous passages, Galileo wrote, "The book of nature is written in the language of mathematics, and its characters are triangles, circles, and other geometric figures. Without these, it is impossible to understand a single word of it." For Galileo, this wasn't a metaphor. It was literal truth. He saw that the motion of falling bodies, the swing of pendulums, and the orbits of planets all followed consistent, measurable patterns. Mathematics, he believed, wasn't just a tool for calculation. It was the grammar of the universe. Galileo began experimenting in ways no philosopher had before. He rolled brass balls down inclined planes, timed them with water clocks, and discovered that distance traveled increases with the square of time, a relationship we now write as d equals t squared. He showed that acceleration due to gravity is constant, regardless of an object's mass, a simple but profound truth that defied centuries of Aristotelian belief. To Galileo, experimentation was sacred. Instead of accepting what the ancients had said, he asked the world directly, and it answered in numbers. He also turned his telescope toward the heavens, revealing mountains on the moon, moons around Jupiter, and countless stars invisible to the naked eye. The cosmos, once divine and untouchable, was suddenly measurable. Each new observation strengthened the idea that the heavens and the earth obeyed the same laws, a radical notion at the time. Mathematics, for Galileo, was the bridge between the terrestrial and the celestial. He didn't merely describe how things moved, he sought to understand why they moved as they did. And though he lacked the full mathematical machinery to express his discoveries completely, his intuition laid the foundation for what would follow: the unification of all motion under a single system. That unification arrived with Isaac Newton. Born in 1643, the year after Galileo's death, Newton grew up in rural England, quiet, brilliant, and often isolated. He studied at Cambridge, but his greatest insights came not from lectures, but during a period of solitude when the plague closed the university and forced him back home to the countryside. There, in the mid-1660s, he began to imagine how the universe might work, not through divine will, but through mathematical law. In 1687, he published Philosophia Naturalis Principia Mathematica, the mathematical principles of natural philosophy. It's a title that captures exactly what it was: philosophy written in the language of mathematics. The Principia was unlike anything before it. Across its dense Latin pages, Newton formulated the three laws of motion, the law of universal gravitation, and the foundations of calculus, though he never used that term. In one sweep, he united the physics of earth and sky. The same force that pulled an apple to the ground also held the moon in orbit. Gravity wasn't a separate heavenly influence, it was a universal law. Everything, from a pebble falling to the ground to a planet circling the sun, obeyed the same equations. This idea was almost unthinkable at the time. For centuries, philosophers had treated celestial motion as something distinct, perfect, unchanging, divine. But Newton showed that the same mathematics that described the fall of a stone could describe the motion of the stars. It was as if the universe had finally been translated into human language, the language of numbers. His equations allowed predictions of astonishing precision. He could calculate how far a cannonball would fly, how a pendulum would swing, how the tides would shift. More astonishingly, his laws explained why planets moved in ellipses, just as Johannes Kepler had observed decades earlier. The heavens were not random. They were clockwork, their gears turning according to perfect mathematical regularity. Yet Newton's mind was as much philosopher as mathematician. He saw himself not as a discoverer of new laws, but as a reader of God's handwriting, someone uncovering the divine order of creation. He famously said, "I frame no hypotheses." He didn't claim to know what gravity was, only how it acted, and that was enough. In his equations, he gave humanity the ability to predict the behavior of the cosmos, to foresee eclipses, design machines, and, centuries later, send spacecraft beyond the planets he once studied through prisms of glass. But Newton's work also introduced something new to human thought, the idea of the universe as a mechanism. If everything followed precise laws, then perhaps the universe was like an immense clock, wound up at the beginning of time, ticking ever since with mathematical inevitability. This view, often called the clockwork universe, shaped philosophy, science, and even religion for centuries. It implied that the cosmos was stable, predictable, and perfectly ordered, a comforting and powerful idea, though one that would later be challenged by chaos and quantum theory. At the same time, another mind was reaching similar conclusions by a different path. Gottfried Wilhelm Leibniz, a German polymath, developed his own version of calculus, independently of Newton. The two men would later argue bitterly over who discovered it first, a dispute that split the scientific world for decades. But their rivalry hid something deeper, a philosophical divergence. Newton's calculus was rooted in geometry, in motion, space, and force. Leibniz's was symbolic, abstract, and elegant, the beginning of modern mathematical notation. His d's and integrals are still used today. Newton saw calculus as a tool to model nature. Leibniz saw it as a language of change itself, a metaphysical framework for understanding the universe. To him, reality was made of infinitely small parts, monads, reflecting the infinite precision of creation. For Newton, truth came from observation and experiment. For Leibniz, it was born in reason. Their debate wasn't just about mathematics, it was about the nature of reality. Was the universe a physical mechanism, running according to external laws? Or was it a perfect harmony of infinitesimal parts orchestrated from within? Between them, they defined the tension that would drive science for centuries, the balance between empirical observation and mathematical abstraction. Regardless of their differences, the consequences were monumental. With calculus, humanity could now describe change itself: acceleration, growth, decay, orbits, waves, heat, sound, light. For the first time, motion could be captured not in snapshots, but continuously, smoothly, infinitely. It was as if mathematics had learned to breathe. From these ideas emerged the framework of classical physics, a discipline built entirely on the assumption that every effect had a cause, every motion a reason, and every event a precise mathematical explanation. The falling apple, the swinging pendulum, the movement of tides, the orbits of moons, all obeyed the same logic. It was a triumph of precision. By the 18th and 19th centuries, Newton's equations had turned the universe into something that could be calculated. Astronomers predicted eclipses centuries ahead. Clockmakers built timepieces accurate enough to guide ships across oceans. Engineers designed machines that harnessed forces once considered divine. Mathematics had become the backbone of civilization itself, and the backbone of reality, as far as we could tell. Pierre-Simon Laplace, one of Newton's intellectual heirs, once imagined a being who knew the position and motion of every particle in the universe. Such a mind, he said, could predict the future and reconstruct the past with perfect accuracy. It would see the universe not as unfolding events, but as a single timeless equation. He wrote, "The present state of the universe is the effect of its past and the cause of its future." To Laplace, there was no room for chance, only the flawless machinery of cause and effect. For nearly 3 centuries, this vision reigned supreme. It built the world of the Industrial Revolution, the age of precision, the age of measurement. To know something meant to quantify it, and the more precisely we could measure, the more control we had over machines, over nature, over the universe itself. But there was something poetic, even spiritual, beneath all that calculation, because in reducing the universe to equations, humanity hadn't made it less beautiful. It had revealed a new kind of beauty, the beauty of inevitability, of seeing the cosmos not as chaos but as harmony. Each planet, each pendulum, each falling apple, all parts of the same grand music, playing endlessly in perfect time. And yet, somewhere deep within that perfection, small cracks were beginning to appear, tiny inconsistencies, anomalies and paradoxes that refused to fit the grand equations. The universe, it seemed, was not as predictable as the clockmakers believed, and soon a new revolution would begin, one that would challenge everything Newton had built and reveal a stranger, subtler truth beneath the ticking of the cosmic clock. When Isaac Newton looked at the heavens, he saw a universe held together by forces acting across invisible distances. Space and time, to him, were the stage upon which events unfolded, absolute, fixed, and eternal. But as mathematics evolved, that stage began to move, and eventually it bent. To understand how that transformation happened, we have to look not at telescopes or machines, but at something abstract, the idea of symmetry. At first glance, symmetry seems simple. It's what we see when 2 sides match, the reflection of a butterfly's wings, the balance of a snowflake, the even rhythm of a heartbeat. But in mathematics, symmetry is far more than beauty. It's a clue to the underlying order of things. It tells us when 2 shapes, 2 states, or even 2 laws of nature are the same under transformation. This is where geometry begins to blur into philosophy. For thousands of years, geometers had studied shapes, circles, triangles, cubes. But in the 19th century, a new branch of mathematics emerged that asked a strange question. What does it mean for 2 shapes to be equivalent? Imagine a coffee mug and a donut. They look nothing alike. One holds liquid, the other sugar. But in a branch of geometry called topology, they're the same. Both have one hole, the handle of the mug, the hole in the donut. And in topology, that's all that matters. You could stretch, twist, or deform one into the other without tearing it. Topology isn't about measurement or angles. It's about continuity, about what stays unchanged even as everything else changes. This new way of thinking began to reveal deep patterns. Mathematics, it seemed, wasn't just a tool for describing the shapes we see. It was a way to understand the essence of shape itself, and that realization began to ripple outward, touching every branch of science. In the early 1800s, a young French mathematician named Évariste Galois made a discovery that would change mathematics forever, and he did it before his 21st birthday. Galois was studying the patterns behind algebraic equations, specifically why some could be solved neatly and others could not. While working through these problems, he noticed that certain transformations, ways of rearranging the elements of an equation, preserved its structure. These transformations formed a kind of mathematical symmetry group. That insight, which he developed in a flurry of genius the night before a fatal duel, became the foundation of group theory, the mathematics of symmetry. It's one of the most powerful concepts ever created. In group theory, We study the ways an object can be transformed while remaining fundamentally the same. A square, for example, can be rotated by 90, 180, 270, or 360 degrees, 4 symmetries in total. A sphere, infinitely more. But these ideas extend far beyond geometry. In physics, symmetry became a way to understand why the laws of nature look the same everywhere, in every direction, at every moment in time. By the early 20th century, this idea was taking on a new meaning. Mathematicians began to suspect that the laws of the universe themselves were born from symmetry, that the consistency of reality was a reflection of invariance. And then one person proved it. Her name was Emmy Noether, and her contribution to science is almost impossible to overstate. Born in Germany in 1882, she faced enormous barriers. As a woman, she wasn't even allowed to formally enroll in university. But her mind was extraordinary. In 1915, she solved one of the deepest puzzles in theoretical physics: why certain quantities in nature never change. Her theorem, now known as Noether's theorem, established a profound connection between symmetry and conservation laws. If a system's equations stay the same when you shift it in time, that symmetry corresponds to the conservation of energy. If the laws don't change when you move in space, that symmetry gives you conservation of momentum. If they stay the same when you rotate, you get conservation of angular momentum. In short, every symmetry in nature produces a conservation law. The universe conserves because it is symmetrical. This was a revelation. Noether had shown that the most fundamental principles of physics, the reasons energy and momentum don't simply vanish, are not arbitrary rules, but reflections of deeper mathematical balance. Symmetry wasn't just a feature of beauty, it was the foundation of reality. Her work quietly redefined physics forever, though she received little credit in her lifetime. Albert Einstein, who admired her deeply, once wrote that she was the most significant creative mathematical genius thus far produced since the higher education of women began. And fittingly, it was Einstein who would take the next great step, transforming geometry itself into the very fabric of existence. Einstein had already shaken the world in 1905 with his theory of special relativity, showing that space and time are not separate entities but intertwined. The faster an object moves, the more time slows down for it. Distances contract. Simultaneity dissolves. But special relativity described only uniform motion, straight lines through space-time. What about gravity, acceleration, and the curvature of motion itself? Over the next decade, Einstein struggled with a question that had haunted physicists since Newton. What is gravity, really? Newton had described it as a force, a kind of invisible pull between masses. But that explanation never said how the force acted, or through what medium it traveled. Einstein suspected that the answer wasn't a force at all, but a shape. In 1915, after years of work and countless mathematical dead ends, he presented the general theory of relativity. Its core idea was astonishing. Gravity is not a force pulling objects together, but the curvature of space-time itself. Mass and energy tell space-time how to curve. Curved space-time tells mass how to move. It was an equation of breathtaking simplicity and depth. To describe this curvature, Einstein relied on a form of mathematics known as Riemannian geometry, developed by Bernhard Riemann decades earlier. A geometry where space could bend, stretch, and twist. In ordinary geometry, the shortest distance between 2 points is a straight line. In curved geometry, it's a geodesic, the path that space itself defines as straight. On the surface of a sphere, that geodesic is a great circle, like an airplane following the curve of the Earth. In space-time, it's the natural trajectory of a planet orbiting a star. Einstein realized that what Newton had called gravity was really the experience of moving through curved geometry. The Earth doesn't orbit the Sun because it's pulled. It follows the natural curvature of space-time around it. The same geometry that governs the orbits of planets also bends light, stretches time, and shapes the evolution of the cosmos. Suddenly, the universe was no longer a flat, fixed arena, but a living fabric, a four-dimensional continuum where every mass, every photon, every second is connected. Space and time became inseparable, woven together by equations of staggering elegance. In those equations, geometry became physics. Mathematics had not only described reality, it had become reality. The predictions were so bold that even Einstein doubted they could ever be proven. But in 1919, during a solar eclipse, the British astronomer Arthur Eddington measured starlight bending as it passed near the Sun. Exactly as Einstein's theory predicted. It was the first direct evidence that space itself could curve. The news spread around the world. Einstein became a symbol of genius, and geometry became a cosmic force. For the first time, humanity saw that the structure of the universe could be written in equations, not metaphorically, but literally. Space-time could stretch, ripple, and fold, and those deformations followed precise mathematical laws. Einstein's equations of general relativity are still among the most beautiful in all of science, not just for their accuracy, but for their poetry. They describe a universe that is dynamic, self-consistent, and deeply symmetrical. At the heart of it all lies the same idea that began with Galois and Noether, that symmetry governs everything. The conservation of energy, the behavior of particles, the curvature of space, all follow from invariances, from the universe's refusal to change its rules as it changes its form. In a sense, the cosmos protects its own logic. From geometry's humble origins in measuring fields and building pyramids, it had grown into a tool for describing stars, gravity, and the flow of time itself. The same mental shapes that once defined temples now define the shape of the universe. And yet, even this profound harmony raised new questions. If space and time are one, and if their geometry curves with mass and energy, what happens on the smallest scales, where particles flicker in and out of existence, where quantum uncertainty reigns? Can geometry survive the chaos of the quantum world? That question would ignite the next great chapter of mathematical physics, one where probability, not certainty, would rule. But for a moment at least, the universe seemed perfectly balanced. A vast, four-dimensional fabric of geometry and symmetry, quietly curving beneath the weight of its own equations. For most of history, mathematics described what could be seen: lines, angles, motion, balance, all things that existed or could be imagined in the physical world. But as the centuries passed, mathematicians began to ask stranger questions, and the answers led them into a landscape that no one could picture. A place beyond reality itself. It began with a simple impossibility: the square root of -1. Try to multiply any number by itself, and the result is never negative. 2 times 2 is 4. -2 times -2 is also 4. So what, then, could possibly multiply by itself to make -1? For centuries, the answer was simple: nothing. The square root of -1 was dismissed as nonsense, an artifact of algebra gone astray. And yet, in their equations, mathematicians kept stumbling upon it. In trying to solve certain cubic and quadratic equations, this strange quantity appeared, as if mathematics itself were insisting that something lay beyond the visible number line. During the 16th century, Italian mathematicians like Girolamo Cardano and Raphael Bombelli began to experiment with these impossible numbers. They called them imaginary, not to suggest fantasy, but because they couldn't be represented by any real quantity. Bombelli even dared to calculate with them, treating the square root of -1 as if it were a legitimate entity. He discovered that these unreal numbers, when handled carefully, produced very real results. Equations that seemed unsolvable suddenly made sense. It was as though mathematics had invented a new dimension. If real numbers could be placed along a line, positive to the right, negative to the left, then imaginary numbers extended that line vertically, forming a plane. Each point on this complex plane represented a number with two parts, one real, one imaginary. Together they created a new kind of arithmetic, one that didn't just measure distance, but rotation. This realization, that numbers could turn as well as move, would change everything. It gave mathematics a new geometry, one that could describe oscillation, vibration, and wave-like behavior with perfect elegance. But it would take another 2 centuries for this idea to bloom fully. In the 18th century, a Swiss mathematician named Leonhard Euler found the key that unlocked the beauty behind these strange numbers. Euler was one of the most prolific minds in history. He wrote over 800 papers, covering everything from fluid dynamics to optics to number theory. But among his countless discoveries, one stands above them all, a small, simple equation often described as the most beautiful in all of mathematics. It reads in words, e raised to the power of I times pi plus 1 equals 0. At first glance, it sounds almost mystical. But hidden within it are 5 of the most fundamental constants in mathematics. E, the base of natural growth and decay. I, the imaginary unit, the square root of -1. Pi, the circle's eternal ratio. 1, the unity of existence. And 0, the void. In a single stroke, Euler showed that exponential growth, rotation, geometry, and arithmetic were all part of the same underlying pattern. Through the magic of complex numbers, addition and rotation became one. It was as if mathematics itself were revealing that all its branches were connected, that numbers and geometry, logic and motion were different faces of the same infinite truth. Euler's more general formula, e raised to the power of I times x equals cosine of x plus I times sine of x, turned out to be far more than poetic. It became a practical tool, the universal translator between the world of algebra and the world of waves. With it, mathematicians could describe oscillations, the movement of strings, sound, light, electricity, using clean, compact expressions. Complex numbers became not just legitimate, but indispensable. Still, it wasn't until the 19th century that they stepped fully into physics. When James Clerk Maxwell unified electricity and magnetism in the 1860s, he did so using a set of equations so elegant that Einstein would later call them the most beautiful in all of physics. In those equations, oscillating electric and magnetic fields intertwined, each giving rise to the other, forming waves that travel through space at a constant speed, the speed of light. To describe those waves, physicists turned naturally to complex numbers. They could represent amplitude and phase, how far along a wave is in its cycle, with a single expression. Multiplying by the imaginary unit no longer meant dealing with nonsense, it meant rotating the wave by 90 degrees. The imaginary number had become a physical operation. In a sense, what had once been heresy had become the heartbeat of electromagnetism. The universe, it turned out, vibrates in complex numbers. Maxwell's equations didn't just explain existing phenomena, they predicted new ones. Before radio waves had ever been detected, Maxwell's mathematics foretold their existence. And when Heinrich Hertz generated and measured them 2 decades later, it confirmed something profound: that mathematics could see ahead of experiment. Equations, it seemed, could tell us about realities we hadn't yet observed. The map was beginning to draw the territory. This predictive power only grew. In the early 20th century, as physicists probed the strange behavior of atoms, complex numbers once again emerged as the natural language of the unseen. When Erwin Schrödinger wrote down his famous wave equation in 1926, the central quantity in it was not a real function, but a complex one, the wave function, often called psi. This function didn't describe where a particle was, but the probability of finding it in a given place, encoded in waves of both real and imaginary components. Only by multiplying it by its own complex conjugate, in other words, squaring its magnitude, could physicists obtain real probabilities. To outsiders, it looked like magic, an imaginary function describing a real universe. But again, it worked with perfect accuracy. Quantum mechanics, built on this strange foundation, became the most precise theory in the history of science. Every laser, transistor, and quantum computer owes its existence to mathematics that was once considered impossible. And this strange relationship between the real and the imaginary became one of the defining mysteries of modern physics. Why should numbers that don't exist in the physical world describe it so flawlessly? What does it mean that the universe seems to obey imaginary mathematics? Even today, no one fully knows. Some physicists argue that the imaginary part of quantum mechanics is just a convenient trick, a mathematical scaffolding. Others suspect that complex numbers are woven into the very fabric of reality, that existence itself is built on rotation through unseen dimensions. But the predictive magic of mathematics didn't stop there. In 1928, a young British physicist named Paul Dirac sought to combine quantum mechanics with Einstein's theory of relativity. He wanted a single equation that could describe the behavior of electrons moving near the speed of light. When he finally derived it, the equation was astonishingly elegant, but it contained a surprise. Among its solutions were not only electrons with positive energy, but also particles with negative energy, entities that had never been seen. At first, Dirac thought he must have made a mistake, but the math was relentless. These negative energy particles behaved as if they were mirror images of electrons, identical in every way, but with opposite charge. A few years later, physicist Carl Anderson discovered exactly such a particle, the positron, the first known form of antimatter. Once again, mathematics had predicted a reality that nature later confirmed. It was a pattern that repeated throughout the 20th century. Equations seemed to know things we didn't. They became oracles of the unseen, revealing the existence of quarks, neutrinos, and even black holes before we could build machines powerful enough to detect them. It was as though mathematics were whispering secrets about the structure of reality, one symbol at a time. This raised a philosophical question that still lingers. Does mathematics simply describe the universe, or does it create it? If an equation can predict something we've never observed, are we discovering truths that already exist, or are we inventing the language that brings them into being? Physicist Eugene Wigner once called this the unreasonable effectiveness of mathematics. Why should abstract symbols written on paper, often invented for their own beauty, turn out to mirror the workings of nature so perfectly? The imaginary unit, dismissed as fiction, had become one of the universe's most reliable tools. Perhaps that's the quiet lesson behind complex numbers. That reality, no matter how tangible it seems, may depend on things that exist only in thought. That truth may sometimes require imagination, literally. The Greeks believed that beauty and order revealed truth. In the modern age, mathematics itself became that beauty, and truth followed. From Euler's equation to Maxwell's waves, from Schrödinger's quantum functions to Dirac's antimatter, the universe continues to confirm what our equations dare to imagine. And as our mathematics grows more abstract, so too does our reach into the unknown. We no longer fear the imaginary, we rely on it. In the shimmering language of complex numbers, we find the pulse of the cosmos, a rhythm that bridges what is real and what is possible. By the early 20th century, science had grown confident. Newton's clockwork universe still seemed solid. Maxwell's equations described light as a perfect wave. Einstein had bent space and time but left their laws intact. It all looked elegant, deterministic, complete. But inside the atom, in a realm too small to see, the order began to break. And what replaced it was stranger, subtler, and far more beautiful than anyone could have imagined. The story of quantum mechanics is the story of mathematics confronting mystery and winning. It began not with equations, but with a problem: light. At the turn of the century, physicists discovered that light behaved like both a wave and a particle. When shining on metal, it could knock electrons free, but only if its frequency was high enough, regardless of its intensity. No one could explain it until Einstein proposed that light came in tiny packets of energy, which he called quanta, later known as photons. It was a radical idea, and it cracked open the smooth, continuous world of classical physics. Soon after, other strange discoveries followed. Electrons in atoms could occupy only specific energy levels, like rungs on a ladder, not a sliding scale. They could jump between these levels, emitting light of precise colors. The atomic world, it seemed, was ruled by discrete numbers, not continuous motion. Mathematics would have to evolve to match it. The first person to give this strange new world an equation was Erwin Schrödinger. In 1926, he wrote down what became known as Schrödinger's equation, a mathematical description of how a quantum system changes over time. It looked simple enough, a wave equation, like those used for sound or water, but its meaning was extraordinary. The quantity it described, called the wave function and symbolized by the Greek letter psi, wasn't a physical wave. It was a wave of possibilities. Psi described every possible outcome at once, the entire range of where a particle could be or how it could move. Only when measured did one specific outcome appear. Until that moment, the system existed in a superposition of states, like chords of probability resonating together. Mathematically, Schrödinger's equation predicted these possibilities perfectly, but conceptually, it defied everything intuitive about reality. A particle was no longer a thing, it was an expression of information, a ripple in an ocean of mathematical potential. At first, Schrödinger himself believed his wave was physically real, like a mist spread across space. But when scientists tried to visualize it, they found that the wave wasn't something you could touch or see. It was purely mathematical. To find the chance of locating a particle, you had to take the wave function, multiply it by its own complex conjugate, essentially squaring its magnitude, to obtain a probability. Math wasn't describing the world anymore. It was describing our knowledge of it. Around the same time, another physicist, Werner Heisenberg, approached the problem differently. Rather than imagining waves, he built a strange new kind of mathematics using arrays of numbers, grids that represented the possible transitions between quantum states. These matrix mechanics, as they came to be called, didn't show a clear picture of what electrons were doing. They simply worked. When Heisenberg calculated the spectral lines of hydrogen, the distinct colors of light it emitted, his results matched experiment with astonishing precision. Later, Schrödinger proved that his wave mechanics and Heisenberg's matrices were mathematically equivalent, two different faces of the same theory. One spoke in the language of waves, the other in algebraic transformations, but both pointed to the same hidden order beneath uncertainty. It was as if nature had given humanity two ways to describe its secrets, one pictorial, one abstract, both perfectly true. But Heisenberg wasn't done yet. In 1927, he formulated the uncertainty principle, one of the most famous results in all of science. It states that the more precisely you know a particle's position, the less precisely you can know its momentum, and vice versa. This wasn't a law of measurement, it was a law of nature. The universe, at its most fundamental level, doesn't permit complete knowledge. Reality, it turned out, was written in probabilities. To classical physicists, this sounded absurd. Einstein himself protested, saying, "God does not play dice with the universe." But experiment after experiment confirmed it. At small scales, particles flicker, tunnel, and interfere with themselves in ways no deterministic equation could predict. Yet quantum mathematics captures every pattern flawlessly. It doesn't tell you what will happen, only what can happen, and with what likelihood. The world, at its root, became a game of chance, but one governed by exact numerical law. The precision of these laws was staggering. Quantum mechanics could predict the color of light emitted by atoms to better than 1 part in a billion. It could explain chemical bonds, electrical conductivity, and the inner workings of stars. And every success strengthened a strange truth, that the universe is both uncertain and exact, a paradox that only mathematics can reconcile. One of the next great steps came from a man who had already helped revolutionize relativity, Paul Dirac. Dirac sought an equation that combined quantum mechanics with Einstein's special relativity, one that could describe particles moving near the speed of light. He succeeded, and the result was breathtakingly elegant. Dirac's equation described electrons with unprecedented accuracy, incorporating both their wave nature and their spin, a kind of intrinsic rotation that had puzzled scientists for years. The components of his equation, called spinors, were complex mathematical entities that rotated not in ordinary three-dimensional space, but in abstract mathematical space. Through them, Dirac discovered something extraordinary, that every particle must have a mirror twin with opposite charge, what we now call antimatter, a prediction born purely from mathematics. A few years later, the positron, the first antimatter particle, was discovered in cosmic rays, exactly as Dirac had foreseen. It was another triumph of the mathematical imagination. Equations, it seemed, could see beyond reality, glimpsing truths the senses could not. By the mid-20th century, quantum mechanics had matured into a vast framework, uniting with electromagnetism to form quantum electrodynamics, or QED. This theory, refined by physicists like Richard Feynman, Julian Schwinger, and Shinichiro Tominaga, described how light and matter interact, how photons scatter off electrons, how forces are exchanged through the quantum field. Its mathematics was fearsome, full of infinite quantities that had to be carefully renormalized, adjusted through ingenious tricks to yield finite physical answers. But when those answers came, they were almost beyond belief in their precision. The magnetic moment of the electron, a quantity predicted by QED, has been measured to agree with theory to more than 1 part in a trillion. It's one of the most accurate comparisons between mathematics and reality ever made. If the thickness of the Earth's crust represented the size of the prediction, the difference between theory and experiment would be smaller than the width of a human hair. That's how precisely the universe follows the script of quantum mathematics. And this pattern keeps repeating. Mathematical structures come first. Physical confirmation follows later. Physicists write equations not to fit data, but to reveal what must be true if the universe is consistent, and then reality obeys. It's as if the cosmos reads the same mathematics we do. Today, quantum field theory has grown into an entire landscape of equations describing not just light and electrons, but all known forces and particles. Every interaction, from the flicker of a photon to the decay of a neutron, can be expressed as a mathematical symmetry, a dance of fields interacting through complex numbers governed by conservation laws first glimpsed by Emmy Noether. The deeper we go, the more it seems that physics is not built on mathematics, it is mathematics. And yet, the strangest thing of all is how abstract it remains. The mathematics of quantum mechanics is so precise, so self-consistent, that even when no one fully understands why it works, it keeps working. Physicists manipulate matrices, wave functions, and spin-ors without always knowing what they mean in human terms, and every time, the universe responds as if it understands them perfectly. It's like conversing with reality in a language we only half comprehend. Quantum mechanics also reshaped philosophy. It shattered the classical notion of certainty, replacing it with probability, and in doing so, it made room for a more subtle form of order, one where randomness and law coexist, where the universe doesn't determine every outcome, but still follows a flawless statistical rhythm. It's a reminder that knowledge itself is limited, that even perfect mathematics cannot remove uncertainty, only describe it with elegance. This, perhaps, is the deepest beauty of the quantum revolution, that mathematics and mystery are no longer opposites. They coexist. The equations are certain, but their meanings are not. And yet, from that uncertainty comes the structure of everything we know: atoms, light, chemistry, life itself. The foundations of our reality are probabilistic, but our understanding of them is precise. In the end, quantum mechanics taught us something both humbling and profound: that certainty is not required for truth, that even in a universe built on chance, mathematics can still predict, guide, and illuminate with infinite accuracy, and that sometimes, to describe reality, you must first accept that reality is not what you think it is. Because in the smallest corners of existence, beneath the atoms and the waves, the universe hums not with certainty, but with probability. And mathematics is the only instrument precise enough to play its song. For centuries, mathematics had been the language of order. From Newton's clockwork to Einstein's geometry, the universe appeared smooth, predictable, and rational. But as the 20th century unfolded, a new truth emerged, one that lay hidden beneath the precision of equations. It turned out that even simple systems could behave in ways no one could ever fully predict, and that chaos, far from being disorder, was another form of mathematics, just harder to see. It began in the late 1800s with a French mathematician named Henri Poincaré. He was studying the motions of three celestial bodies, a problem that seemed, at first, purely mechanical. Newton's laws could predict how two bodies orbit each other perfectly, but add a third, and the equations become tangled beyond solution. Poincaré found that even a tiny change in the starting conditions, a shift smaller than the blink of an eye, could lead to completely different futures. The paths of the planets diverged wildly, their orbits twisting and folding through time like tangled threads. He realized that this wasn't a flaw in mathematics, it was a property of nature itself. Deterministic systems could still be unpredictable, not because they were random, but because their sensitivity to initial conditions made long-term prediction impossible. It was the first glimpse of what we now call chaos theory. Poincaré wrote, "It may happen that small differences in the initial conditions produce very great ones in the final phenomena." A poetic understatement of one of the deepest truths ever found. For decades, his insight lay dormant. Mathematicians preferred systems they could solve, and chaos, by definition, resisted control. But in the 1960s, a meteorologist named Edward Lorenz rediscovered it by accident. Lorenz was studying weather patterns on one of the first digital computers. His model was simple: a set of 12 equations describing convection, the rising and falling of warm air. One day, to save time, he reran a simulation starting from a rounded set of numbers, 0.506, instead of 0.506127. When he returned, the new run had diverged completely from the original. The weather, in his model, had evolved into something entirely different. A rounding error, smaller than a breath, had changed the entire future of the system. Lorenz realized that this sensitivity wasn't a glitch, it was inherent. He visualized the behavior of his equations as a shape in 3 dimensions, a strange, twisting curve that never intersected itself, looping endlessly without repetition. He called it an attractor, and it became known as the Lorentz attractor. It revealed that chaos was not random at all, but structured, an infinite pattern of motion confined within invisible boundaries. From this discovery came a phrase that would enter popular culture: the butterfly effect. The idea that the flap of a butterfly's wings in Brazil might set off a tornado in Texas. It wasn't meant literally, but symbolically. In chaotic systems, small causes can lead to enormous effects. Weather, climate, population growth, ecosystems, all of them dance on the edge of predictability, governed by deterministic laws that unfold into complexity beyond calculation. And yet, even within chaos, mathematicians began to find patterns. The shapes that appeared in Lorentz's data resembled other patterns seen in nature. The jaggedness of mountains, the branching of trees, the swirling of smoke. They seemed irregular, but never random. In the 1970s, another mathematician, Benoit Mandelbrot, gave these forms a name: fractals. Fractals are structures that repeat themselves at different scales. Zoom into a coastline, and you find smaller coastlines hidden within. Zoom again, and the pattern continues, seemingly without end. Mandelbrot realized that traditional geometry, with its lines, circles, and perfect solids, couldn't describe the roughness of nature, but fractal geometry could. He coined the term the geometry of roughness, the mathematics of clouds, mountains, rivers, and galaxies. With the help of computers, Mandelbrot visualized these shapes, feeding simple recursive formulas into early screens that glowed with infinite complexity. The most famous of them, the Mandelbrot set, revealed a shape that spirals inward forever, its boundaries endlessly detailed, echoing itself on every scale. It became a window into infinity, generated not by chaos, but by astonishing simplicity. A few lines of code could produce an entire universe of form. Fractals changed how we saw nature. They explained why lightning branches as it does, why blood vessels form networks, why ferns and snowflakes repeat their shapes. They bridged the gap between order and disorder, showing that chaos has structure, that complexity arises naturally when simple rules interact over time. It's the same principle that governs everything from galaxies to ant colonies. Today, chaos and complexity theory extend far beyond physics or mathematics. Biologists use them to model the heart's rhythm, the spread of diseases, and the dynamics of ecosystems. Economists apply them to markets, where small decisions ripple outward in unpredictable ways. Neuroscientists find fractal patterns in the firing of neurons, in the architecture of the brain itself. Everywhere we look, the same mathematical fingerprints appear: repetition, feedback, emergence. The lesson of chaos is that predictability and order are not the same. Even when outcomes can't be forecast, the underlying process can still be understood. Mathematics doesn't give us control, but it gives us vision, a way to glimpse the shape of the unpredictable. In a way, chaos theory brought mathematics full circle, back to its earliest purpose. Just as ancient people marked the changing of seasons without knowing why, we now map the turbulence of weather, the motion of populations, the rise and fall of complexity itself. We still can't predict every future, but we can recognize the rhythm behind them, the hidden geometry of change. And perhaps that's what makes this chapter of mathematics so profound. It reminds us that not all beauty lies in order. Sometimes it's found in the delicate edge between stability and chaos, where the universe stops being predictable and starts being alive. Mathematics has always promised certainty. From Euclid's flawless proofs to Newton's perfect mechanics, it seemed to offer an escape from confusion, a world built entirely on reason, where truth could be known absolutely. But as the modern era unfolded, that dream began to tremble. Mathematics, it turned out, was not infinite perfection. It was a fragile creation of the mind, one capable of brilliance, but also bound by limits it could never cross. Those limits first appeared in the oldest mystery of them all, the prime numbers. Primes are the atoms of arithmetic, numbers that cannot be divided by anything but themselves and 1. 2, 3, 5, 7, 11. They're simple to define, yet maddeningly unpredictable. As numbers grow larger, primes appear to thin out, scattered among the composites like stars fading into the darkness of space. And yet, they never vanish completely. There are infinitely many of them. Euclid proved that more than 2,000 years ago, but no one has ever found a perfect formula that predicts where they'll appear. Mathematicians have hunted for patterns in their distribution for centuries. They know, on average, how often primes occur, roughly following a curve called the prime number theorem, but the precise rhythm of their appearance remains elusive. In 1859, the German mathematician Bernhard Riemann proposed a bold new way to understand them. He extended the idea of numbers into the complex plane, numbers that have both real and imaginary parts, and defined a mysterious function, now known as the Riemann zeta function. Its zeros, the points where it equals 0, appeared to hold the secret pattern behind all primes. Riemann conjectured that all of these non-trivial zeros lie perfectly along a single line, a line where the real part equals 1/2. If true, this alignment would explain the distribution of primes with near-perfect precision. It became known as the Riemann hypothesis, and it remains the most famous unsolved problem in mathematics. Over a century and a half later, no one has proven it, though it's been checked for billions of cases, and no counterexample has ever appeared. Its truth would not only unlock the secrets of prime numbers, but ripple across physics, chaos theory, and cryptography. Primes are woven into everything from quantum mechanics to the encryption that protects digital communication. They are randomness made lawful, chaos hidden beneath order. The Riemann hypothesis is one of 7 Millennium Prize problems, a list of the most profound open questions in modern mathematics. Each carries a reward of $1 million, though money is not what drives those who chase them. They are pursued for the same reason explorers climb mountains, because they define the edges of what is known. Among them are questions about the smoothness of fluids, the behavior of quantum fields, the geometry of higher dimensions, each one a doorway between mathematics and the physical universe. But unlike mountains, these problems have no clear summit. They are horizons, always visible, never reached. And behind them all lurks a deeper mystery, one that no proof can resolve. It appeared in 1931, when a young Austrian logician named Kurt Gödel published 2 theorems that shook the foundations of logic itself. Gödel had been part of a movement inspired by David Hilbert, a mathematician who believed that, with enough rigor, all of mathematics could be placed on a complete, consistent foundation. Hilbert's dream was to formalize everything, to show that every mathematical truth could, in principle, be derived from a finite set of axioms using pure logic. It was the ultimate quest for certainty. But Gödel quietly proved that this dream was impossible. He showed that in any system powerful enough to describe arithmetic, there exist statements that are true, but cannot be proven within that system. In other words, no matter how perfect your logic, there will always be truths it cannot reach. He also proved that such a system can never prove its own consistency. Mathematics could no longer guarantee that it rested on unshakable ground. The implications were profound. It meant that there is no final proof, no ultimate theorem that explains everything. Even mathematics, the most rigorous creation of the human mind, contains mysteries that lie beyond proof. It's not that we haven't found the answers, it's that some answers are forever unreachable. The universe of logic, like the universe of stars, extends beyond what we can see, Gödel's incompleteness theorems didn't destroy mathematics, they made it human. They reminded us that the pursuit of knowledge is endless, and that even in a realm of pure reason, humility is necessary. They also echoed strangely through physics, for just as mathematics discovered its limits, so too did the physical sciences. Quantum mechanics revealed uncertainty in measurement. Relativity showed that even time depends on perspective. The deeper we dig, the more we find boundaries, not because the universe hides them from us, but because they are built into the structure of existence itself. Some physicists have even noticed eerie parallels between number theory and the quantum world. The energy levels of certain atomic systems, for example, follow statistical patterns nearly identical to those of the Riemann zeros. It's as if the primes themselves hum with the same music as quantum particles, the abstract and the physical sharing a hidden rhythm. Mathematics and physics, though separate in form, may be two languages describing the same song. These connections have inspired some of the boldest speculation in modern science that the universe itself might be a mathematical structure. That matter, space, and time are not merely described by equations, they are equations. Every particle a term, every law a symmetry, every event a computation unfolding across reality's fabric. If that's true, then the mysteries of mathematics, the primes, the hypotheses, the incompleteness, aren't just intellectual puzzles. They are reflections of the universe's own nature, infinite, intricate, and forever incomplete. And yet, there's something beautiful in that incompleteness. Because without it, curiosity would end. If mathematics had no mysteries left, there would be nothing left to explore. The Riemann hypothesis, Gödel's paradoxes, the millennium problems, they are not failures of reason, but its greatest gifts. They remind us that knowledge is not a destination, but a horizon, one that moves as we move. In the end, mathematics, for all its power, remains a kind of music, precise, eternal, but never finished. Each theorem is a note, each discovery a phrase, part of an infinite symphony that began long before us and will continue long after. Its themes repeat, evolve, and intertwine, echoing across centuries, always incomplete, yet always expanding. Perhaps that's why mathematicians speak of beautiful proofs and elegant equations, because deep down, they know that mathematics is not just about truth, it's about creation. We may never find the final answer, but perhaps we're not meant to. Perhaps the beauty lies in the chase, in the unending attempt to bring order to the infinite, in the realization that even at the edges of knowledge, there is harmony. And that within the silence of the unknown, mathematics still plays on. For all its precision, all its power, mathematics still leaves us with one question that no theorem can answer. A question older than geometry, older than proof itself. Did we invent mathematics, or did we discover it? It's a question that divides philosophers as sharply as it unites scientists. To Plato, mathematics was eternal. Not a human creation, but a realm of truth that exists independently of us. Numbers, he said, are not made, but found, timeless forms that exist in a perfect abstract world, unchanging, awaiting discovery. When a mathematician finds a new theorem, they are not inventing it, but uncovering a truth that was always there, like an explorer revealing land that has always existed, just unseen. For Aristotle, mathematics was different. He believed it was a tool, a language invented by the mind to describe the world. Numbers and geometry were abstractions distilled from experience. They had no existence outside of human thought. In this view, mathematics is as human as music or poetry. Powerful, yes, but born of imagination. And yet, something doesn't quite fit with that second view. Because again and again, mathematics has proven capable of describing things we've never seen, even predicting them long before discovery. Imaginary numbers, once dismissed as nonsense, turned out to describe quantum mechanics perfectly. Non-Euclidean geometry, dreamed up as an intellectual curiosity, became the foundation of Einstein's relativity. Equations written centuries before the technology to test them now guide spacecraft, model DNA, and predict the curvature of space-time. It's hard to believe this is coincidence. Mathematics seems to know the universe better than we do. This strange fact has long troubled philosophers and physicists alike. In 1960, the Hungarian-American physicist Eugene Wigner wrote an essay titled "The Unreasonable Effectiveness of Mathematics in the Natural Sciences." He asked a simple but profound question: why does mathematics, an abstract creation of the human mind, describe the physical world with such astonishing accuracy? Why should equations invented to explore ideas later turn out to predict reality? Wigner pointed out that mathematics often works far beyond its intended purpose. When Newton invented calculus, he designed it to describe motion. 3 centuries later, it describes the spread of disease, the behavior of light, and the expansion of the cosmos. Equations that began as mental experiments now run the engines of modern civilization. There is something uncanny about it, as if mathematics were not a human language at all, but the universe's own handwriting. Some thinkers believe that's exactly what it is. They see mathematics not as a description of reality, but as reality itself. In this view, sometimes called mathematical realism or Platonism, everything in the universe, from atoms to galaxies, is a manifestation of mathematical structure. Matter and energy are simply expressions of geometry and symmetry, interacting according to rules that exist outside of time. To discover mathematics, then, is to glimpse the architecture of existence, the source code of being. Others resist this idea. They point out that mathematics has changed throughout history, that our concepts of number, infinity, and space have evolved. Early humans couldn't even conceive of zero. The Greeks refused to accept negative numbers. Imaginary numbers, infinity, and higher dimensions were all once dismissed as absurd. If mathematics were truly eternal, would it have needed invention after invention to grow? Perhaps then mathematics is both discovered and invented. A dialogue between the universe and the mind that observes it. When we invent new mathematical ideas, we are expanding the language through which reality can speak back to us. We give form to possibilities, and the universe either echoes them or remains silent. When it echoes, when a formula written on paper turns out to describe a particle or a galaxy, it feels less like invention and more like revelation. And now, in the age of machines, that dialogue is changing again. Mathematics is no longer confined to human intuition. Algorithms can now explore patterns too vast for us to imagine. Artificial intelligence can discover relationships between numbers and data that no mathematician could find alone. In a sense, we have built new minds to think mathematically for us. Minds that don't seek beauty or meaning, only truth hidden in structure. Already, AI has found proofs that eluded us, optimized designs that surpass our imagination, and simulated universes governed by equations of staggering complexity. It has no need for intuition, only computation, and yet the results it finds are still mathematical, still part of the same vast structure that connects everything from quarks to quasars. It's as if we've handed the universe the pen, and it continues to write through us, and now through our creations. Some physicists and philosophers believe this might be the next stage in our relationship with mathematics. Not the end of understanding, but a new way of exploring it. Humans, limited by our senses and imagination, can only glimpse small regions of the mathematical cosmos. Machines may wander deeper, into dimensions of logic we cannot yet perceive. If mathematics truly reflects reality, then artificial intelligence may be our newest instrument for listening to the universe's hidden harmonies. But there is still something uniquely human about mathematics, something that no algorithm can reproduce. We don't just calculate, we wonder. We feel beauty in equations, symmetry in logic, emotion in structure. We sense meaning in patterns that may have none. That blend of reason and awe, of cold precision and quiet reverence, is what turns mathematics from mere calculation into art. Perhaps that's the point. Mathematics, like music, is a bridge between mind and world. It exists both inside and outside us, half discovery, half invention. We build it, and it builds us. It shapes how we see, how we measure, how we understand. And through it, we approach something far greater, not just the mechanics of the universe, but its poetry. In the end, whether mathematics is discovered or invented may not matter, because either way, it connects us to something infinite. If it is discovered, then we are explorers in a timeless landscape, travelers tracing the contours of eternity. If it is invented, then we are creators of worlds, artists painting existence with logic and number. And perhaps, in truth, it is both at once, an act of creation that reveals and revelation that creates. The deeper we go, the more we see that mathematics isn't separate from the universe. It is the universe, reflected through the lens of consciousness. Its symbols are our way of touching the infinite, of giving shape to mystery. And every equation, every pattern, every number is a whisper from that infinite horizon, reminding us that the universe is not just something we observe, but something that is thinking through us. So as this journey through mathematics draws to a close, imagine for a moment that quiet rhythm beneath everything, from the pulse of atoms to the spin of galaxies. It's the same rhythm that hums in the human mind when we calculate, when we wonder, when we dream. A universal language, older than words, without beginning or end. And as long as there are minds to seek it, mathematics, that mirror of the cosmos, will go on reflecting itself endlessly into forever.